Hello, hi. It's my first time in Switzerland, actually, so I'm excited to be here. So, my name is Kai. I'm reasonably active in the Laravel community. I've done some open source, and I shitpost on Twitter. So, if any of those sound interesting, like feel free, or don't. Anyways, so database indexing. Are you excited about database indexing? Like the saddest type statement. Cool. So database indexing, it's obviously a pretty broad topic. And my experience has been that developers often have a very sort of superficial understanding of database indexing, and I have been one of those developers. So where we have some rough understanding of it makes queries faster, I guess, right? And if a query is slow, then I just kind of look at the where clause and then just throw an index at everything that appears there, and I hope that one of them works. That's usually, I've literally been that person, and I have worked with people who are like that, which is what inspired this talk. At the same time, I think we all agree that slow queries are one of the biggest performance killers in an app, right? If a query is slow, the app just grinds to a halt, especially if it gets called a lot. So it's a topic that is really good to know something about, but at the same time, in my experience, a lot of developers don't. And so my goal with this is, the way I kind of think about it is there's two ways when you learn a topic about how you acquire knowledge. So first one is sort of gaining understanding. And so that means you basically just, gaining understanding just means knowing that a certain fact is true. It's basically memorizing, right? And then the second thing is gaining insight. So gaining insight means you know why something is true and how it relates to other things. And that's kind of the knowledge I hope to pass on to you here. Because I think just memorizing situations isn't a good way to go about this, because then you are very reliant on basically having every possible situation memorized, because as soon as you encounter something that you're unfamiliar with, you're just screwed, right? Because you don't actually know how this stuff works. I want to go the other way and hopefully give you a good foundation about how database indexes actually work behind the scenes, what the database is doing. So you don't have to memorize stuff. So you will be able to look at a situation and just go, oh, I see, the database has to do this thing, which is slow because of that. And so if I make this change, right, the database can use this other strategy instead, and sort of kind of work through the example without having to already know the solution ahead of time. So that's still pretty ambitious. So let's see how I do. Luckily for us, I don't have to fit this into a 30-minute conference slot, so I can take my time a little bit more here.
2 hours.
No, it's not going to be that bad. Cool. So before we go into the more technical parts, let's just think about really quickly what an index is on a more conceptual level, right? Because an index isn't really a database concept. It's not even a technical concept, right? If you take any nonfiction book and you go to the back, more often than not, there's a literal index in there, right? It's an ordered list of keywords that appear in the book, together with the page number where that appears, so you can quickly find it again without having to go through the entire book again. And really, that's what an index is. At its core, an index is simply an ordered representation of the index data. The key word in this sentence is ordered. And to understand why order is so important, it's kind of like the whole identity of an index. Let's do a quick example. So I'm going to show you 2 separate lists of names. They're going to contain the same names, they're just arranged differently. And you're supposed to find the same name in both of them, and then we'll see which one was easier, right? So the name I want you to find is Kaneko, all right? So here's the list of names. Try and find Kaneko. That's all the time you have. Here's list number 2, and try and find Kaneko again. So which one was easier? That's a rhetorical question. It's this one. It's the second one, right? The one that's sorted alphabetically. But why? We intuitively understand how to use an ordered list to quickly find things, but what exactly is it about order, about an ordered representation, that makes it so much faster? How does this change our, let's say, search algorithm, right? So if we go back to the unsorted list, and I just want you to appreciate how fucking annoying this transition was to make, because I had to move every single name by hand. first I had to sort them in some external tool and then just go, okay, where is the name, and then move it to the correct position. So I know like this is enough names to where the unsorted list just is awful to use. Anyways, so if we have an unsorted list, then pretty much by definition, the name we're looking for could be literally anywhere, right? That's what unsorted means. So really our only chance in this case is to start at the first name and then simply go through all of them in order until we hopefully eventually find what we're looking for. The worst case scenario would be the name doesn't appear in the list at all, in which case we have to go through the entire thing just to figure out it isn't there. So this obviously doesn't really scale particularly well because it sort of scales linearly with how many names are in the list, right? Your worst case is always looking through everything. So if we add 1 million names to this list, the worst case scenario just becomes looking at 1 million names more, right? Because it could always be the last one, or it couldn't be in the list at all. So this doesn't really scale particularly well. Let's see what changes with the sorted list, because that's not how we do it in this case, right? We know that the name Kaneko starts with the letter C. At least you know that now, right? So if that's the case, we're not going to start at A, right? We're not going to go here. We're immediately going to jump to the part of the list that contains the names that start with the letter C, right? And we don't even look at anything before that. Sure, we might have to glance at them just to see A, B, B, C, okay, here. But we didn't actually read any of those names, right? You wouldn't be able to tell me any name that starts with A because you didn't actually look at them. And the same goes for the other end of this like range, right? As soon as we hit the first name that starts with a D, we also know we're done. It cannot be in this part of the list, right? Because now every name starts with a letter that comes after C, which means these are the only names we even have to look at. It doesn't matter how long the entire list is. It only matters how small we can make this subset. So even if we add 1 million more names, if those 1 million names don't contain a single name that starts with the letter C, we still only have to look at those 3, right? This range doesn't change, and this is the important thing. So what order gives us is it allows us to make an assumption about the position of the thing we're looking for inside this list, right? So instead of having to look at everything, we can immediately jump to the relevant portion of the list and only look at what's absolutely necessary instead of looking at everything. This is why order is so important. And this is literally, not just similar to, literally the same for a database index. It's exactly the same concept. A database index just allows the database to only look at what's absolutely necessary instead of having to look at everything, thereby kind of decoupling ourselves from how long the entire list is down to, well, how big is this subset of things that are relevant to me, right? Which makes them scale really well. Cool. So now the question is, how do databases actually implement this, right? Because this is a nice visual way for us to understand it, but if you just have a big sequential list of things, you can't just jump to this position in the list, right? Because you don't know where it is. So we need some data structure that allows us to quickly navigate to the correct portion of the list. And this is what we're going to spend the majority of the talk on, is this data structure. And so this data structure is called a B tree. So 2 quick asides. 1, there are other type of indexes, right? There are full text indexes, spatial, GIN, GIST, there's a bunch of them. The B tree index is like the 99.5% case. If you create an index and you don't specifically tell the database to create a different kind of index, you're going to get one of these. Second aside here is that technically, what we're going to see here are B+ trees. I've decided to ignore this distinction for the purpose of this talk. Most literature also just calls them B trees. Just so you're aware, this is mainly here to cover my ass, so someone doesn't come up to me afterwards and go, well, actually, I am aware of this. It's just a meaningless distinction for us. That's why I decided to keep it simple, so I have to explain the difference between them. Okay, so what does a B tree actually look like? It looks something like this. So unsurprisingly, it is some kind of tree structure, right? In this case, I have flipped the tree on its side just because it's easier to fit on a 16:10 slide that way. You usually have them top down. But it's some kind of tree structure. And this tree is sorted. And so the way it is sorted is if you start at any nodes. So each of the blue rectangles is called a node. And if you start at any node, at any of the numbers, and you follow, in this case, the line up, then that subtree will only contain values that are smaller than the one you started at, right? And if you go down, you will only find values that are greater than or equal to where you started at. So please convince yourselves that that's the case, right? And so in this way, the tree is sorted, right? We're not going to go into like how this gets constructed, because this isn't about how to implement a B tree. It's more about how does the database use it and what are sort of the performance implications of that. So the nodes in a B tree, or in any tree for that matter, have different names depending on where they appear in the tree. So the one on the very left is called the root node. Every tree has exactly one. That's kind of one of the defining characteristics of a tree. Otherwise, we just have a graph. The ones in the middle are called internal nodes, or intermediate nodes, or branch nodes. There's a bunch of names for them. You can have multiple layers of them. In this case, we only have one layer. And then finally, the ones on the very right are called the leaf nodes. We're primarily interested in those leaf nodes. So the leaf nodes in a B tree, you can see like these two arrows connecting them, right? The leaf nodes of a B tree form a doubly linked list, right? So there's always a pointer to the next leaf node and to the previous leaf node. So technically speaking, there should be an arrow here pointing to null, right? What this doubly linked list allows us to do is we can traverse through those leaf nodes by following this chain without ever having to go back up the tree again once we hit the end of a leaf node, right? If this doubly linked list wasn't there, as soon as we hit the end of one leaf node, we'd have to go back up to the parent node and then find the next one and then keep scanning. Not the most efficient thing to do, especially because we're going to do this a lot. This scanning through the leaf nodes is going to be our bread and butter. So having this available to us is really useful. The numbers inside the nodes are called keys, and they don't have to be numbers. These are the actual values from the column that you put the index on. So if you had an index on an email column, then these would just be email addresses, right, instead of numbers. What's interesting about the keys in a B tree specifically is that they have an additional piece of data stored on them. They have a pointer back to the row in the table where this value comes from. I'm being intentionally a bit vague about what this pointer is because different databases implement this in different ways. In MySQL, at least, if you're using InnoDB as your engine, which you should, then this will just be your primary key that MySQL will just include on every index you create. But this could also be a purely database internal value. The point is that using these pointers, no pun intended, we can relate each of these values from the tree, from our index tree, back to the corresponding row in the actual table, right, where it comes from. This is useful if we ever have to go back to the table in case we have to load any additional data, right? What? Okay, so that's my quick intro to B trees. We're going to come back to this throughout the talk, but this is more the general overview so you know what they look like. So now let's look at some examples. So for all of these examples, I have pre-recorded the examples because I don't want to live code this, and the queries can take quite a while. But all these examples are ran against a table that has 50 million rows in it. Which, by the way, 50 million rows is not a big table. It's not a small table, but it's at least an order of magnitude below what the database can very comfortably handle. You can probably add like 2 zeros to that before it starts to get interesting. But it is enough to where you actually have to start thinking about indexing, right? If you just don't ignore indexing 50 million, you will feel the pain. But the database can definitely handle that, no issues. So the first query we're going to look at is this one. We want to count the number of users that have between 10,000 and 20,000 followers. So currently, the table doesn't have any index on it, right? I just created a table, seeded it, that's it. So if we run this query as is against this table, it is going to take roughly 5 seconds to execute on this machine over there. 5 seconds is an eternity for a database, right? With databases, we're often like aiming for like low millisecond, like single-digit millisecond or like 10 to 20 milliseconds. Like that's our, sometimes even sub-millisecond, right? Like that's what's possible. 5 seconds is glacial. So if we have a situation like this where we have a query that's a tad slow, how do we actually figure out what's going on here? Because the thing about SQL, right, is that it's declarative. We only tell the database what kind of data we want. We don't tell it how to retrieve it. That's kind of a black box for us. But if you want to understand what's going on here, why is this so slow, we need to understand what's going on. And the way we can do this is by looking at the so-called execution plan. So the execution plan is essentially the database's way of telling us how it decided to, well, fetch you the data that you requested, right? So databases have a thing called the query optimizer. And the job of the query optimizer is basically looking at your query and then evaluating a bunch of options on how it could retrieve the data that's described by this query, and then it's trying to pick the best one. And the execution plan is telling us which one it decided to pick. So it's kind of our way of looking into the database's brain, right? This is unfortunately also the part of the talk where I can't avoid becoming a little bit database specific, because these execution plans look different for pretty much every database system. However, the information they're trying to convey, the concepts they're trying to convey are the same. It's just that they use different terminology to describe the same thing. They have different textual representations. I'm going to use the MySQL explain output just because it's the one I'm most familiar with and the one I have installed. If you use, for example, Postgres, you just have to do a little bit of extra work to look up what's the Postgres equivalent of this MySQL thing, but then everything I'm going to talk about is going to apply the same to Postgres as well. Luckily, the way you get these execution plans, as far as I can tell, is the same for every database. You just take your query, you plop an explain at the beginning of it, and you run it. So this doesn't actually execute the query, right? This doesn't run. It just does the sort of the query optimizer trying to figure out what it's going to do and shows that result. So if you run this, we get a result that looks a little like this. I'm using the JSON output of MySQL's explain statement here because, one, it is significantly better than a table-based one, and it fits better on the slide. I've also cut this down quite significantly. There's a lot more data on this if you just run it. I've decided to focus on the thing that's most relevant to us, that sort of gives us the most bang for our buck. And far and away, the single most important piece of information on this execution plan is this access type. So the access type tells us two things. It tells us, are we using an index at all? And if so, how are we using it? And these two things together basically is what cause your query to be fast or slow, right? Understanding this will tell you pretty much all you need to know about why a query is slow or fast if you understand what they're trying to communicate to you. So in this case, the access type says all. That's kind of the worst case scenario. So access type all is called a full table scan, which is pretty much as bad as it sounds, right? We're not using an index at all. Instead, we're loading the entire table, every row, every column, and we're just going through everything one by one. This is us looking through this unsorted list of names, right? It's the same situation. We don't know where the data is. We just have to start at the beginning and just go through everything, which kind of explains why this took 5 seconds, right? We have 50 million rows. That's quite a lot of work to do. Also, fun fact, this is the only access type in MySQL that's written in all caps. All the other ones are just lowercase. So I find that kind of interesting. Interesting design choice, yeah. Yeah, it's like avoid at all costs, yeah. Okay, so now we know we're not using an index. Makes sense because there is no index, but that also explains why it takes 5 seconds, right? There's just a lot of data. We have to look at everything. So how can we improve this? Well, this is where we start adding indexes, right? And so usually people just look at the query, look at the where statement. There's followers there. That's where I'm going to put the index. It's not the worst strategy, so let's just try this for now. Because the query doesn't really reference any other columns, so that's the only thing we really can put the index on. So if we do this, we're putting an index on the users table and the followers column, right? The stuff in the parentheses is the column, and this, before that is the table. When we run this, what happens is that the database is going to take the values from the column you specified in the index. And then it's going to construct this B tree from these values, right? This is our index. when we say create index, this is what's getting created. This is literally what the index looks like, a smaller version of it, right? And again, this is the same tree I showed before, right? We can now see it is sorted. If you just look at the leaf nodes, right? Smallest value, biggest value. So now the database has this thing available to use. So let's see what happens when we rerun the same explain statement now that we have added this index. So if we rerun this, we can see that it changed quite significantly. So there are two more pieces of information here. We have this possible keys and key. When you see key, just think index, right? It's the name of the index. So possible keys is what's called the index candidates. It's what the query optimizer has, the indexes the query optimizer has identified as being potentially useful. But it could use them. And there can be more than one. And then key is the index it actually picked from that list, because it can only use one. So in this case, it makes sense. We added one index, right? It saw it, it picked it. As a consequence, our access type is no longer all, because now we're using an index. It changed to range. And this is probably like the most important one to understand. That's why I'm focusing on this, on this specific access type in this talk, because it illustrates the concept the best of how the database uses the B-tree. Range is what's called an index range scan. So how that works is if we have our query, and for some reason I changed the range from 20,000 to 30,000, but doesn't matter. Here's our index. There's two parts to the index range scan. The first is what's called a B-tree traversal. This is essentially starting at the root node and then trying to find the beginning of a range, right? So in this case, the beginning of our range is 10,000. So if we think back to this like list of names, when we had a sorted list of names, we jump to like the part of the list that starts with the letter C. This is now like the B-tree equivalent of this, right? So we're looking at, this is the beginning of our range. Any value that has a followers count less than 10,000 can't possibly match. And because the tree is sorted the way it is, right, we can traverse through the tree either going up or down, depending on if we're looking for a smaller or larger value. And now we're basically at the point in the leaf nodes where anything before that point can't possibly match, right? Those are the names with A and B. We don't even have to look at them. This B-tree traversal is instant. Like, it doesn't matter if you have 5 billion entries in here, because this is essentially just binary search, right? It doesn't matter. This will always be instant. So once we're there, now it's the second part of the index range scan, which is the actual range scan. So now we're inside the leaf nodes. We're going to look at every key in this node, in these nodes, and we're going to compare them against our query. And if it matches our query, it becomes part of the result set. And as soon as we hit the first key that doesn't match our condition, we know we can stop, because anything beyond that point can't possibly match, right? This is like the names that start with D and so on. So in this case, we matched 3 rows, and we only had to look at a total of 4 rows if we count the last one that didn't match, right? It doesn't matter how big this entire tree is. If this condition only matches 3 rows, we will always only have to look at 3 rows. It doesn't matter how many rows we have in the table total, right? Because the B-tree traversal already eliminates potentially millions of rows. Like anything before that point, we didn't even have to look at, right? We just get that for free as part of the B-tree traversal. And then we only scan as far as we need, and then we immediately stop. So this is why, this is like the database version of us going through the ordered list of names, right? This is how it's implemented on a technical level. And this scales really, really well. So that's on range scan, index range scan. Let's look at a different example. Let's say we want to count the number of followers for all users that have been created after a certain date, because that's a useful metric and not just me running out of examples, right? So we can skip ahead a little bit, because we know we haven't added an index on created at, so it's just going to be a full table scan, right? Like there isn't an index, it has to do a full table scan. It's going to take like 10 seconds. So let's skip over that part and immediately jump to the same thing we did before, where we added an index to followers. So let's do the same thing for this created at column, and let's see what changes. Now if you run the query that's with that index on created at, if you run this query, it still takes like 8.5 seconds, which is really weird. Like this is the point where it starts to become unintuitive if you don't actually know what's going on behind the scenes, right? Because this seems to be the same situation as before, but it behaves completely differently. It gets even weirder if you look at the explain statement to understand what's going on, because this shows we're doing a full table scan for some reason. So that explains the 8.5 seconds. The real question, though, is why does possible key show our index? Like the database has recognized, yes, there is an index. I saw that. For some reason, I decided not to use it. And this just looks like a bug, right? Like if you don't know what's going on, this is strange behavior. But it makes total sense. In order to understand this, just to prove a point, you might be tempted to just overrule whatever the query optimizer has come up with and just say, no, use that index, trust me, right? So the way you can do this in MySQL, and this is like do not try at home territory, is you can use the force index directive and then give it the name of the index you want it to use. And now if you run it, holy crap. The query isn't done, by the way, I just stopped recording at that point. So if we force it to use the index, it takes at least an order of magnitude longer than the full table scan, which only took 8.5 seconds. This is just, what is going on here? If we look at the explain statement, when we force it to use the index, because we can do that, right? We can say, give me the execution plan if I were to make you use that index. It's strange because everything looks correct, right? It's a range scan. We just learned that they're good. Why is this so slow? It's using the index. Everything looks fine. It's just the query itself is like beyond repair, right? So to understand why this happens, we need to actually look at what data gets stored on the index. So here's what our B tree for this created at index might look like, right? So now we have dates instead of just these follower numbers. And the first part of this index range scan is going to work exactly the same way. We're going to do the B tree traversal. We're going to find the point in the leaf nodes, right? That's the beginning of our range that we have to scan. We compare the first key. In this case, yep, that is part of that matches my condition. So this should be part of the result set. But now what happens? If we look at these keys, this only contains the data from the created at column of the table, right? Because that's what we put the index on. That's fine because that's what our where condition references. However, our query also references the followers column. That doesn't exist on the index, but the query needs it. So where does it come from? Well, it comes from the table, right? This is where this pointer back to the table comes into play. Because once you've identified that, yes, we're interested in this row, we now have to go back to the table, read this row, so that we can then take whatever columns we need that aren't on the index. And it has to do that for every row that matches that condition. Every time you see the database like flash, that is one read from disk, one random disk access. In this case, it's only about 6. In the actual query I ran, it was about 20 million, because that's how many rows my where condition matched, which is also the real reason that I stopped this query, because it was destroying my SSD. So the problem here is that, so the database has correctly decided not to use the index, right? Because it could tell that I'm going to have to read from disk 20 million times. That is awful. But there's still like one thing that's a little unintuitive, because you might think, well, isn't the full table scan even worse, right? Because we have 50 million rows in that case. Well, no, because the database is smart, right? Like it knows that if it has to do a full table scan, it knows it has to read everything anyways. It's not going to do it one row at a time, right? It's going to read them in big batches. So yes, you have to look at more rows overall, but you're performing significantly fewer reads from disk, and that's the real bottleneck in this case. And we can see like it's a really fucking big bottleneck, right? So this doesn't mean that the index is bad, by the way. The index is perfectly fine. The problem just is that this query just matches too many rows. The index doesn't change that, right? That would be terrible if it changed our result. It just helps us find these rows faster, but if it matches 20 million rows, well, it matches 20 million rows. That's not going to change by using an index. If we were to, let's say, change our where condition to like narrow our range so it matches fewer and fewer rows, at some point the database will actually use the index. Because at some point, the trade-off of, yes, I'm going to have to read from disk a couple times more, outweighs the reading everything and scanning through it, right? There's some point where the scales tip, and this becomes more efficient, and the database is pretty good about figuring out like where that point is, so don't mess with it too much. So that's kind of the issue that's happening here. But that's still kind of unsatisfying, right? Like, do we just have to accept that this query is just always going to be slow? Is there nothing else we can do? Well, if the problem is that we have to go back to the table because the index doesn't contain all of the data that the query needs, what if we put it on the index, right? The galaxy brain moment, yeah. So let's do some cleanup first. Let's remove all the indexes we've created so far. So we're back to just the clean slate table. And now let's create a new index on both created at and followers. Now if we rerun the same explain statement, now that we have this index, this other index, we can see that the database will now voluntarily use the index. It's going to do a range scan, all without having to do force index, right? Because now the index actually contains all the data that the query needs. It doesn't have to go back to the disk at all. This kind of index is what's called a covering index. So I want to explain this a little bit because I think the terminology is a little ambiguous because it makes it sound like you can just create a covering index, right? It's a property of the index. That's not the case. An index is covering for a specific query. It's not covering on its own. That doesn't make any sense, right? The same index can be covering for one query and not covering for another query. It purely depends on, does the index contain all the data that the query needs, yes or no? Then it's a covering index. Covering indexes are really fast because an index is usually just kept in memory, right? And so if you have all the data you need on the index, it means the entire query can be performed purely in memory, right? And reading from disk is like orders of magnitude slower than reading from an index. So they're like a really powerful kind of index, but it depends on the fact that you have all the data on the index. And if you have like a select star query, right, then just forget about a covering index because you have to put the entire table on the index, which just defeats the purpose. But it's like a good tool to have for these sort of like aggregation queries where you're just like summing something, where you basically only access a few rows, then this could be a good tool to have in your tool belt. So what we just did, there was some animations here that I missed. Okay, yeah, cool, range, nice. So what we just did is we created what's called a composite index or a compound index or a multi-column index. And I want to spend some time on these because I think people get confused by them a little bit. And it's really like due to no fault of their own. It's mostly because of how we tend to teach them. Because when you read about composite indexes, you're usually just presented with a bunch of rules you have to memorize about in which situation can a query use what part of a composite index and when can't it. And these rules seem very arbitrary, and you just asked to memorize. And as I said in the beginning, I don't want you to memorize. I just want you to understand why these rules are the way they are. It's not that complicated. And understanding composite indexes is actually quite important for a point that's like at the end of the presentation. So let's look at them a little bit more in depth. So first, let's try and visualize what a composite index actually looks like, because I think this is kind of the first point where people lose the plot. Because even if you know like the B tree, what does a composite index look like, right? Like how does that fit into do you have more nodes? Like how does that work? So when we create a composite index, like in our case on created at and followers, the database is going to take the values from this column in the order that we specified, right? We said created at and then followers. This is important, and we'll see why in a second. And then it essentially just concatenates them together. You can basically just think of this as one big string now. Obviously, in reality, it's slightly more complicated because you have different data types and whatnot, but honestly, this isn't very far from some of the implementations out there. As far as like your intuition for this stuff goes, you just did like an array.join here, right? And now you just have one big string with some delimiter that delimits the individual columns. And now we're sort of back to the situation we had before. We just have one value per row. So now we just build the B tree from this long string. And notice this tree doesn't have any more nodes, it doesn't have any more keys, the same row doesn't appear multiple times, it's just that each key gets a little longer. And now what's interesting is if we look at the values in the leaf nodes and we look at how they are sorted, that basically tells us everything we need to know in order to understand composite indexes. So the way this is sorted is these rows are sorted first by the first part of the key, right? The created at part of the key. We have the smallest date on top and then the most recent date at the bottom. And then for all rows, for each group of rows that have the same date, those are then sorted by the next part of the key, right? That's kind of like the tiebreaker between them. What's important is, and this is like the last step that people kind of miss a lot of the times, is if we only look at the second part of the key, this isn't sorted, right? This goes all over the place. And this might not seem like a huge thing, but like it's only once we add back in the first part of the key, the second part of the key is only sorted with respect to the previous part of the key. Only for rows that have the same value is that sort of the tiebreaker. And this generalizes to no matter how many columns your multi-column index has. So in general, it's like every new part of a key is only sorted for rows that have the same value in all of the previous key parts. So if you have A, B, C, D, then the D part of the index, grow up, the D part of the index is only sorted if you have the same value in A, B, and C, right? It just becomes more and more specific. And again, this doesn't seem like a huge insight, but it's actually crucial. We now know everything there is to know to understand why multi-column indexes behave the way they do. So let me give you a few examples. One of the rules you might learn about composite indexes is that the order of the columns in a composite index matters, meaning an index on A and B is not the same as an index on B and A. Well, of course it isn't, because what happens if we change the order of the columns? We get a list that's sorted completely differently. Like, sure, it has all the same data in it, but this is a completely separate list, right? And since order is kind of the whole point of an index, it's like the identity of an index. If you change the order, by definition, you have a different index. So the order has to matter in this case, right? This isn't some abstract rule. It's just, of course it does. Another thing you might learn is that you can use an index from left to right, but you can't skip columns. Again, it's not the most intuitive thing in the world if you don't have this sort of, visual intuition for it. But we already saw what happens when you skip a column. The rest of the index loses its order, right? This isn't sorted on its own. As soon as you skip a column, then the rest of the index is basically just back to being unsorted. So of course you can't skip columns. To illustrate this, let's look at this example. So let's say we want to select all users that have more than 20,000 followers, or like greater than or equal to 20,000 followers. Does this index help us? Because remember, when we do a range scan, an index range scan, we want to find the beginning point of our range, but we're only referencing the second part of the key. Where is the beginning point of that range? Right? There isn't any. This isn't a sorted list. We're back to being unsorted. It's only once we add back in this created at part, the previous part of the key, that these rows that we match by the created at condition actually become sorted. Only in this case can we use the next part of the key. So as soon as we skip one, that's it, right? We can't use the rest of the index anymore. And then lastly, this is my favorite one because it's just so obscure, is you can use an index from left to right until the first range condition. And this is like, when you first read it, it's like, okay, sure, right? I'm just gonna accept that because it's not really intuitive how a range condition would affect this until you start actually like trying it out. So let's take this query from before again. Here we have an equality operation on created at, right? The first part of the key. We have an equality operation here, and then an inequality operation on followers. So what we can then do is we take the first part of the key, the created at part, and we basically use that to limit, to sort of do a first pass on limiting how many rows we actually have to examine, right? Because these rows, any row that matches this query has to satisfy both constraints, right? And so we already know that every row that matches, it has to be one of those. Anything outside that doesn't really matter, right? But now look, the rows we are left over with all have the same value for the created part, which means the next part of the key is sorted. So we can do the same thing again for the followers column. So we just use that to further limit how many rows we have to look at, and we're already just left with one. Just to be clear, this is all before we ever start scanning through the leaf nodes. This is all part of the B-tree traversal, right? We're immediately jumping to this part because we're able to use both parts of the key. So when I say use an index, what that means specifically, because I think that's a little ambiguous what that means. When we say use an index, it means you can use that portion of the index to narrow your range before you have to start scanning, right? And in this case, we can use both parts of the index to narrow our range because of this relationship, right? The first one matches only rows that have the same value, so we can do the same thing again. Now look what happens when we change this query from created at equals to created at greater than equals, right? So now we have our range here. And basically, range is sort of anything that's like any inequality, right? Greater than, less than, in between, everything that matches more than one value, essentially. So what happens now is, let's try and do the same thing again. We're going to try and use the first part of the key to limit our rows. So we're still going to start here. But now we don't have an upper bound anymore, right? So there's no, like the endpoint is just the rest of the list. Anything from this point on. Notice something with this list. We now have multiple distinct values for the first part of the key, right? They don't all have the same created at date, which means the next part of the key is unsorted. So when we say we can't use the index, that means we cannot use the follows column to further reduce this range. These are all the rows we will have to examine. So in this case, we can use the created at part as part of our B-tree traversal, right? It gets us to this point. But then the second part of the condition, we have to apply as we're scanning, right? We can't already do it in this, at this stage. So as I mentioned before, the B-tree traversal is instant, right? So we want this to be as sort of selective as possible, right? So you want to be able to use as much of the index as possible because you basically skip a whole bunch of your data pretty much for free. If you're still left with 20 million rows after like the B-tree traversal, you're going to have to look at 20 million rows, right? And then apply whatever conditions are left as you scan. And that's pretty much it. Like, this explains everything there is to know about multi-column indexes, like why they work the way they do, why you can sometimes use them, and why you can't sometimes use them. Like, this isn't black magic, right? You can show this with an Excel sheet. It's like, just here's 2 columns, sort them, just try it out. As soon as you do it the first time, you go, ah, shit. Right? Yeah, like it goes back down here. Oh, okay, I see. Right? As soon as you recognize it, it's like, yeah, of course. Now you don't have to remember this weird rule about like the first range condition. It's just, no, it's, right? It hopefully makes sense why it's that way. So there is actually an exception to this because Stefan asked me. I'm going to just mention this here because we have time. If I go back to this, to the first, which example was it? The one where we skip columns. Oh. Transitions going backwards are painful. Which one is it? No, that's not it. The order. Yes, this one. Come on, come on. It's not as cool the second time around. Okay, this is the query, right? Where we said, okay, we're skipping this column. This is true. Like this, as far as like knowledge and understanding of how indexes work, this is good to know. This is correct. However, there are exceptions to this where databases have kind of found a way to work around this a little bit. So in newer versions of MySQL, I don't know exactly which version, but when I ran my examples again, like a couple years later, this example all of a sudden started doing a range scan. I was like, this is not how this is supposed to work. I didn't understand why this was working. And then I had to research a little bit. It turns out there's a clever trick you can use here that some databases might use. So when we're skipping this, this column, the database can use what's called an index skip scan. What that means is, yes, we're ignoring the first part of the key, but we can basically we can sort of partition this list into these subgroups that all have the same value, right? Instead of treating this as one big list, we say, okay, these two values have the same, right? So we treat them as one, and then we do an index range scan just on those two. And then we go to the next group and do it just on this one. Because that allows you to potentially skip rows for each of those groups, right? So that's an index skip scan. That's why you will sometimes, even though you have a query like that, you might see access type range. And in this case, I think the MySQL explainer output has like an extra column, which is the worst thing ever, because it's like so difficult to understand. Sometimes it just says using where, and you're like, no shit, like what? But why isn't this always there, right? And in this case, I think it would say like using index skip scan or something like that, just so you're like aware, like there are optimizations about this, but they are optimizations. Like by default, this would work the way I described it. So now we have to wait 30 seconds while I, you know what, I'm just gonna, oh shit, it's not mirrored. Where's my cursor? I'm just gonna use the arrow keys. Whoa, spoiler, okay. Play. Right, so the reason I spend so much time on composite indexes is because they're actually pretty important to understand when you want to design reusable indexes. So the thing to realize is an index isn't free, right? Yes, indexes make reading faster, often quite significantly so, but they do have an impact on writing. And maybe you now have like some understanding of why that is, right? Because you have these B-tree structures for every index on the table. And every time you insert, update, delete, those also have to get updated. And because of how B-trees work, they might have to be rebalanced, right? And if you have a bunch of them and they're pretty big, you know, that can have an impact. So the rule of thumb is kind of to say you want to have as many indexes as necessary, but as few as possible, because they aren't free. In order to have as few as possible, you obviously need some kind of way to write an index that's reusable, meaning more than one query can benefit from this index. And that's usually where composite indexes come in, right? Because as you add more data to the index, you open it up to more queries that can potentially benefit from it. But in order to design like a good multi-column index, you need to be able to understand, well, which query can actually benefit from this? What if I change the order? Okay, then this can actually use the first two key parts, but this can only use the first one. Well, which of these queries is more important to me, right? Like this one runs 10 times a second, this one runs once a month, then screw that one, right? I'm just gonna prioritize this other one. And I know how the composite index would have to look so that it would benefit like maximally from it. Well, at the same time, you still know, okay, this other one can still, you know, benefit from the first part of the key. That's still good. Instead of having like a one-to-one mapping for every query to an index, that's not a good way to do. You start to design these multi-column indexes. But if you don't really understand like how they get accessed and how useful they are for a particular query, you're basically just guessing, right? So that's why I kind of focused quite a bit on that. Okay, so we are, I think, 20 minutes over time. If this was a conference, it was the last time I'm speaking at that conference. They would have like yeeted me off the stage 10 minutes ago. Yeah, this is, punchline, hey. And so yeah, thanks a lot for listening. If you have any questions, feel free to ask me. But that's all I have.